Okay, I think we're ready to get started. Hi, my name's Krste Asanovic. Welcome you to the third Chisel Bootcamp. This is actually the third one we held, basically about one every year since we started doing Chisel. I thought it'd be good to just quickly give people a bit of context and background to Chisel. So some of the background was a while ago, back in 2005, we started this RAM project to use FPGAs for multiprocessor emulation. This is at a time that multi-cores were happening. And in architecture work, it was really difficult to do any realistic simulation on multiprocessors. It just took too long. And so came the idea of using FPGAs to accelerate simulation models. And over the next bunch of years, we had a bunch of success building various prototypes, including here at Berkeley. The RAM project was a multi-university consortium collaboration. But here at Berkeley, the things we built were this 1000-core RAM Blue, which was an early proof of concept. The 64 RAM Gold shared memory many-core we built inside PowerLab. And then recently, Zhongji Tan just completed his thesis, and he built a 3,000-server emulation engine called Diablo, which modeled execution-driven simulation of 3,000 servers running Linux and communicating over switches. These are all great, but these are really only simulators. They really could only model machines at that scale, and it took a lot of effort to design these in Verilog. So really heroic hardware FPGA design efforts to build these simulators. So these are not prototypes as in directly mapping a hardware design. They're actually simulating multiprocessors. So that was actually a lot of work, and these were just simulators. For a long time, my group has been building processors. So there's a long history of building different kinds of VLSI processors all the way back to the early days T0, Vector IRAM. I did the scale at MIT, and then with this Raven chip here at Berkeley. And for the VLSI processor projects, what usually happens is you kind of design down to a fixed design point, and then you're happy that that works, and you build it. And this was also a lot of heroic design, but basically only a few fixed hardware design points, and no real high-level simulators were built for these designs. They really kind of focused on getting the one thing working. And part of the problem we had is linking this, wanting to do design space exploration, but not wanting to have to redo all the work when it came to actually building a design, fabricating designs. So what we were really after was sort of one description for design space exploration and for actual synthesis, actually building the final result. And we wrote a proposal back in 2009 to DOE to work on this. There was interest from the DOE, and the motivation there was they wanted to explore future exascale architectures using ramp-style technology. But one of the target applications he had was this green flash system. The idea there was if it's going to take many tens of megawatts to run a supercomputer, that the electricity bill there is pretty expensive, so maybe it's better to spend some of that money designing a more efficient chip and save energy. And so they were the idea was to build a green flash custom supercomputer that was custom designed for running climate codes. So the idea was to explore the large design space, including auto-tuning the software onto the hardware, and then actually fabricate chips that could be part of this exascale supercomputer. Looking around, realize that the core of all this approach, if you want to really integrate synthesis with simulation, is you'd really like to have a single hardware description language that could cover both spaces. And it sort of surveyed what the existing scenery of hardware description languages was. You could see there was existing HDLs, the common ones like Verilog and VHDL, but very low level, very clumsy to describe certain things, and also closed source. So we couldn't really get good open source versions of those that we could go and modify and add all the tools and other features we wanted to add. Now, there were other languages used for simulation that were open, like, for example, System C became popular during this time. But although many people tried, it really was too far from synthesis. And I know there's a new effort to try and push this, but it really is not a very good language to synthesize from, though it's quite common today in industry to use this for simulation. Another effort I was sort of partly involved with at MIT was BlueSpec, Samburst and MIT. This was a much better, higher-level hardware description language, but it was closed source. There's a company spun out to do this. And it really encoded a particular model of computation, guarded atomic actions, which is great, I would say great for describing some kinds of hardware, but not the best at describing all kinds of hardware. And finally, a lot of people over the years have been looking at what we call application to gates synthesis, where you have some end application in mind, some kind of signal processing typically, and then you write descriptions in a high-level language, you map, and eventually gets turned into a microarchitecture, sort of high-level synthesis. And this is effective at some things, but a lot of domains it's really ineffective. For example, building a programmable processor. This is not what you want to do if you want to build something that not only does exactly one thing well, but that you can program to do many things well. So it's really kind of out of the domain of this kind of language. Right, so you see all those different needs, and the existing ones that were around there at the time didn't really meet this need. So then we were fortunate when, in 2010, Jonathan came by, and he was interested in working with us, and he's a language expert, and so Jonathan has really been a lead in pulling together his Chisel project, which you'll hear all about today. So Chisel stands for Constructing Hardware in a Scala Embedded Language, and we have our goal now of having a single description that we can map down to fast simulation on just regular CPUs, just compiling through C++, or fast emulation using FPGAs, or actually building chips with it. So this is kind of what we wanted to do. And for those of you who've been around the last couple of boot camps, there's a bunch of new features in Chisel 2.0 that you hear about. There's a bunch more that we're working on that you'll probably also hear a bit about to extend Chisel further and increase the range of things you can do with it. But like Chisel, basically we embed the hardware description language inside a full programming language, and this lets us do many, many things. So it's easy for us to add new tool-like functionality to things we develop because we have control of the whole description and the language, and it's easy to build very powerful generators so we can do this design space exploration quite extensively. And as you hear later, we can also layer up those domain-specific languages to get closer to that application-to-gates functionality, even though that's not the basis of the base part of Chisel. I thought I'd also just give you a bit more context about where is Chisel going now. So we started this new project called Aspire. It sort of launched February this year, the new lab. And this is looking at where's computing going in the next bunch of years. And really the goal of Aspire is to try and figure out how to keep computers' performance and energy efficiency improving despite the fact that transistor technology scaling is really slowed down and pretty much stopped. So this is a chart taken from a DARPA study that basically illustrates this problem. These are decades down here. This is system capability in some abstract log scale. And CMOS has been great. It's been growing tremendously, but now it's sort of hit this fallow period. And there's no real new savior device technology out on the horizon. All the things in the labs are far off from competing with CMOS because CMOS gives you, billions of transistors reliably interconnected, clocking at gigahertz, and just for a few dollars per part. And there's really nothing out there that's going to take over in the next 15 to 20 years. So we hit this problem of, well, transistors aren't getting much better. How are we going to make computers better? And Aspire, our goal is to really to work on everything above the transistor to make things better. And this is following on from the Power Lab, which officially ended in May this year. There's a book now you can go download from. You can actually get the PDF free from Microsoft, or you can pay the minimum amount at Amazon, $2.99, to get a Kindle ebook for this thing. So Aspire is a new 5-year project that builds on some of the Power Lab successes. So some of the things builds on the patent-based software architecture to describe programs, communication avoiding algorithms to minimize the amount of data you move around, which is a key constraint for most performance and energy efficiency. CGITs to specialize particular patterns of computation down to the system implementation. And finally, Chisel is a very big part of Aspire. Sort of thought of throw up the whole Aspire, what we call the lasagna stack, just to kind of show you where Chisel fits in. So this kind of takes you from applications all the way top, all the different layers of the system down through to the hardware down here. But we see Chisel playing a part of two ways in Aspire. One is that we're interested in trying out new kinds of processing architecture. ESP is kind of meant to replace current applications processors using specialized engines to run code more efficiently, general purpose code more efficiently. And Hurricane is a new spatial computing fabric we see as replacing the accelerators you have in modern SoCs. But we also see, conventional CPUs, GPUs, and FPGAs and ASICs are also targets. And so one way you might use Chisel is to go from those applications down through onto, for example, a spatial computing fabric, FPGAs, or building your own special chip for an application. The other way we're thinking about using Chisel is we're experimenting with new architectures. So we write these architectures in Chisel and actually implement them using Chisel as well. So we use Chisel to implement our processors. We also use starting to use Chisel to actually map applications down onto these computing fabrics as well. One other thing I'll mention that's going along with Chisel is as part of all this work, we've decided to do our own ISA we call RISC-V. And RISC-V is highlighted and bolded. The main thing is it's an open ISA. We guarantee not to sue you if you implement RISC-V, though somebody else might if you embody one of their patents. So based on a lot of experience with other ISAs, we decided the main thing we need to do is come up with our own and build a world around that, and that's what we've been doing. And it's actually, the base part of it's simple enough to use in education, but it's a realistic ISA you'd actually want to implement. So we have a bunch of experience building chips with this. We've got a growing software ecosystem, GCC, Linux, glibc, Python, and several real implementations. And all the implementations are actually written in Chisel. So we use Chisel to write the RISC-V cores and implementations. And actually, we've made available initially what we call SODOR educational cores. These are cores written in Chisel we use in classes where the students can actually play around with the internals of an architecture design in the class. And Chisel makes it possible to do that, whereas if you threw Verilog at them, they'd spend the whole semester trying to figure out what Verilog means and debugging that. So Chisel, we found, even for undergraduates taking their first serious architecture class, Chisel descriptors of hardware is really fine. So the RISC-V ISA 2.0 spec is almost ready. It's quite a bit different from 1.0. It's almost done. This will be out in the next couple of weeks, I expect. One other thing we'll be doing in Aspire is pushing on the idea of agile hardware development. So this goes along with this theme of wanting to explore a large design space and quickly produce chips. And so what we've really been trying to do is figure out how can we do this. It usually takes years to bring out a new processor chip. And part of it is the idea of using generators to build the chips. Another part is looking at agile software best practices from software and trying to translate that to hardware design. And what we've been trying to do is actually push complete designs all the way through to layout regularly instead of once every 6 months or every year. Every few weeks, try and get the whole design mapped down to layout, and then incrementally add features. So we always have something that will go through the whole flow and produce real chips. So we've been trying to do this over the last year or so and had some success. We're still working on making this actually a reality, but we think this is the way hardware has to go. You want a very quick turnaround of designs if you're going to have pervasive hardware. So the Aspire project, what we see is specialized engines are really the only way forward to improve energy efficiency. So we've got to figure out how to do those more quickly. And so that's, we've been trying this agile hardware strategy. And we've been pretty successful. This is just in the last 2 years. The group has pushed out a bunch of real processors in 28 nanometer and 45 nanometer. And these are some of these gigahertz class processor tape outs by a small group here. And these were, except for this one, they're all written in Chisel. This was the Raven one. This was done in pre-Chisel. But the rest of the designs have all been written in Chisel, mapped through a regular tool flow, produced chips through regular foundries, and running it over gigahertz in these technology nodes. Okay, so that's really all I wanted to say, give you a brief context background where Chisel fits in. I'll talk about the agenda today. So Jonathan's going to start the tutorial in a minute and have a break at 10:30. The breaks will all be outside in the foyer where you were at registration. There'll be a box lunch at 12:30, and in the afternoon, Jonathan, there'll be more hands-on session. There'll be little hands-on pieces during the tutorials, but then later on in the day, you'll get to do more intensive work. Then an important piece of this is at 4 o'clock. What we'd like to do is get feedback from you about Chisel. So this is our way of, getting input from, broader community people about what you like about Chisel, what you don't like about Chisel, what things you would like to have added, what's missing. So really, this is really important for us to get feedback from you about what you'd like to see in Chisel. We'll officially close at 5, and then unofficially, people who want to, we're going to meet up down at Jupiter in downtown Berkeley for informal drinks and food. For those who want to head down there, so that's at 5:30 downtown Berkeley. It's right next to the downtown Berkeley BART station, and there'll be enough people going down there. You can, if you don't know where it is, you should be able to attach yourself to a group to head on down there to see it. Okay, so finally, I just want to thank all the different sponsors who paid for the Chisel work. I'll just leave that slide up there. So any questions before I hand over to Jonathan? Yep.
Quick one. You said that the new ISA is going to be an open architecture. Are you implying that there is some writable control store capability, or open in a different sense?
So it's a RISC architecture. So it's interesting you mentioned writable control store. So the one of the SODOR cores is actually a microcoded version of RISC-V. And there's actually a microcode compiler in that repo. So you can actually write new microcode for the data path we have for RISC-V. Though that's not the intended, the ISA is designed for hardware implementation. We just include that as part of the educational course so people learn how to do microcode. Okay. All right.